Okay, let's start our lecture today. And last week, we already talked about the introduce the concept or the definition of stationarity and non-stationarity. And for time series data, we like to have stationary data, okay? And today, I'm going to continue that example and sort of just a little bit review, but I'm using one of the data set. I'm not going to explain it in detail of this data set since I will go back to this data set next time for another topic, okay? We just look at using this data set, and now that's a sort of briefly review in order to introduce the concept, the new topic we are going to cover, which is co-integration and also the ECM models, okay? All right, and this is the data, let me just call it, it is an exam, the data about, okay, this is the exchange rate between the US dollars and the euros, okay? And since this is time series data, and it covers from, it's daily, from January the 4th, 2000 to May 8th, 2008. So it covers 8 years and several months. So it's a lot of data. It's more than 2,000 data. It's daily data, okay? We're looking at that as I saw this, we look at this as a variable, okay? The name is LNEX. I'll explain that next time, okay? All right? So first of all, if we want to check whether this variable is stationary or not, okay? There are several ways. The first way is look at the graphical. Okay, so look at this graphical. This is the graphical analysis. Look at the data like this. This is the time, okay? And this is the LNEX. How do you see from this graph? Some of them drifted down, then drifted up. Okay, so this is not, it's a typical example for not non-stationary, okay? And so if I check with, this is the leg 1, okay? For axis is the leg 1, and for the vertical, Y is original LNEX. So look at this one. How do you think? It's really highly correlation, right? Okay, so we can see from ACF. Okay, this is what we call autocorrelation function. What's the definition of autocorrelation function? It's like the coefficient is like this. So this means the kth lag, okay? This is the current, and this is a k coefficient, correlations. So in general, this one, the relationship is like this. Okay, so if this is high, means the autocorrelation is high, right? Therefore, we can see the autocorrelation function. Look at this one. This is autocorrelation function. This one. Did you see that the correlation is pretty high from 0.998 until the lag up to 36 or 30, even in 30 is in 0.95. So it's highly correlated, okay? Then another one you can see is from, how many lags do we have to see, or how many legs we choose to see the correlations. Usually we can by some criterion. Okay? Yes. Of all, yeah, like you do the Python, you use all, okay? And in business area, usually we use 1/3 or 1/4 data. Okay, so in this case, I have more than 2,000 observations. So if I want to see the lag for 1/4, it should be 500. But now I just look at just only 30 and 36, even though the correlation is still very high. Okay, and there's another way to see is look at partial autocorrelations. Look at this one. Okay, by the way, this autocorrelations, the hypothesis testing is by this Q statistics, and the probability is this. So look at the probability is very small, right? So the null hypothesis is no autocorrelation. Alternative is autocorrelation. So this p-value is very small. Means what? Means highly correlated. We reject the null hypothesis with no correlation, right? Okay? So, and what's the difference between partial autocorrelations? Look at partial autocorrelation function. Okay, the difference between partial autocorrelation function and the autocorrelation function we can think about. We learn this multicollinearity issues, right? And we look at pairwise comparison. And the other one is partial correlation. Okay? So this is like something like the partial correlation, the idea of partial correlation. So if you look at the diagram, not diagram, it's the formulas. Okay? So this means that if I have AR1, then this KK, is something like this one. If K is greater than 1, this is 0. And since this AR1, the lag is 1, so this one is alpha. So the difference between autocorrelation and partial is autocorrelation. If I want to look at the relationship of the lag 1 and lag 10 for autocorrelation is also considering the relationship in between, I mean from 2 to 8. But partial autocorrelation can control the from 2 to 8. Just only look at the relationship by 1 and 10. That's the difference. So one is control the rest of the lag in between, and the other one is doesn't control it. Okay? All right? So look at this one. And so if we look at this one, okay, the partial autocorrelation function, the first one is pretty high, and it reduces. Okay? You understand what I'm saying here? Okay? All right. So this is, so we have introduced the two ways. One is graphical analysis. The other one is looking at the correlation function, either autocorrelation function or partial autocorrelation function. And the third one is we just introduced last week. We see the unit root test. So we use the Dickey-Fuller test to do all the unit root test. Okay? And I'm not going to talk about the unit root test, okay, since we have done that last week. Okay, now let me go over to some other definitions which I didn't cover last week. Okay, this is all digging fuller test. Okay. Here. Okay, let me see. All right. Since we know that we have the time series data which is non-stationary, okay, then is there any other way to make it stationary? After we do those tests, okay, either graphical test, either autocorrelation functions, and either unit root test, it didn't pass it, means we have non-stationary time series data. And what do? Is there any other way to make these variables stationary? Is there any other way? Okay, the first of all, we're looking at the detraining. I mean, detraining means if this is a variable we're working with, right? So I'll put the equations like this one. Detrain it means I put the t as one of the variable. Okay? All right? So after I detrain it, then I will have residual. After I detrain it, then I have the residual, means I regress A5. I regress A5, then I store the variable of the A5 and running the test of the residuals to see whether the residual is stationary or not. If it is, means after I detrain it, the variables get rid of those trending informations or trending factors. The rest of them will be stationary. Okay? Understand what I'm saying here? Okay? So if it is, and look at this one, okay? I'm using those LNEX and detrain it, okay? How do you think? Then let's look at so this is the way I detrain it, use the time, okay? Then I have the residual, and I'm using that residual to do the, this is the residuals plot. How do you think this plot? Does this graph look like? This is the U, means the residual, okay? Regress the A5, and this is the residual from A5. How do you think this graph is non-stationary, right? Okay, this one is pretty similar to the one we see it for the original data. Understand what I'm saying? It means that it doesn't work in this case. After I detrain it, the original variable still contains the non-stationary factors in it. Okay? So this means, okay, so I'm going to introduce some terms. Okay? We say that if a time series becomes stationary, if we detrain it in a manner suggested, it's just I did, okay? It is called trend stationary process. Okay, this usually, you can see from the time series, the literature of the time series data. Okay, this is called trend stationary process. Means after I detrain it, then the variable this time series becomes stationary data, and we call it trend stationary process. So actually, trend stationary process, before we train it, it is still non-stationary. Then after trend, it becomes stationary. So this is different from unit root process. Okay, unit root process is to check in whether it is stationary or not. And the second way, okay, if the trend doesn't work, is there any other ways? Usually the second way, or the very common way, is take the first difference. What do you mean by first difference? Means the difference between the continuous two observation. Okay? All right? So second way is, instead of detraining time series in the manner suggested, suppose we take the first difference. Okay? So first difference usually by notation of delta. Okay, delta. Okay? So look at this. This is the D1, means the difference between these two time series data. Okay? So what do you see from here? The D1, the graph of D1 becomes this one. Okay? And if we look at this is the autocorrelation function and the partial autocorrelation function of the difference, the first difference. First difference means a difference once, means first difference. Okay? All right? So look at this autocorrelation function and partial autocorrelation function. What did you see? Look at this correlation coefficient, and look at this and the probabilities. So if we check this first difference, actually it is stationary, right? Look at this p-value. It is stationary. All right? And partial autocorrelation is no correlation at all. Okay? Any questions so far? All right. So usually, if we do the first difference, and most of the time, according to the experience of practical experience, usually first difference will make the series stationary many times, most of the times. Okay? Right? So look at this. If you do this Digger-Fuller test, okay, this is reject the null hypothesis. Means what? There's no unit roots, right? Okay. All right, and so that's this another terms. If a time series becomes stationary after we take this difference, the difference, then we call a time series difference stationary process. So it's DSP. Okay? This is taking the difference to make the series stationary. So we call it difference stationary process, DSP. Okay, this is different from D-trend. So TSP is trend stationary process. Okay, and sometimes you will see from the literature that we need to identify what the data is, DSP or TSP. So if a time series is DSP, means take the difference, but we regard it as TSP, and it is called under differencing, because it should be take the difference, but there you consider regarded as a TSP, therefore under differencing. Okay? On the other hand, if the time series TSP, but you treat it as the DSP, then this is called over differencing. Okay? And there's some terms I wanted to introduce, which is pretty highly related to the time series data and also some forecasting terms, okay? The first one is integrated time series, okay? In a time series literature, we often come across the term is called integrated time series. And if the time series becomes stationary after differencing it once, then it is said to be integrated of order 1 and denoted by I parenthesis 1. Okay, this is the usual terms. And if it has to be difference d times, when we say difference d times means difference in difference. Okay, so in d times, then we denote it by I over d, parenthesis d. Okay, this is the universal definition in time series literature. Okay, so therefore the term stationary time series and time series integrated of order 0, since if it is a stationary time series, there's no integration, so we put it I0. Okay, so this is stationary time series. Okay? Okay, so let's sort of review what do we mean by this. So when I say I0 means it is stationary time series, and mean reverting. When we say reverting means converge. Okay? And fluctuates around its mean with constant variance. And autocorrelation in a parallelogram decline to 0 very rapidly as the lag increase. Okay? And if it is, take the first difference, means this is a stationary time series only after taking the first difference, and meanders widely without, if you didn't take the first difference, original data meanders widely, okay? Then can drift away from mean permanently and is said to have a stochastic trend. And if you see the autocorrelation in a parallelogram, decline to 0 very slowly, just like the first autocorrelation we see just a few minutes ago. Okay. All right, and so that's some of the terms and also the concept about the time series data I need to make up, to cover whatever we need to know. Okay? All right, any questions about these parts? This is not really in our textbook, okay? But, it's the general concept which you need to know, okay? All right, yes? You mean this parts? Copy of that. Okay, sure. I'll put it in the iLearning. Okay, this part, okay? All right, and this is the, okay. What I'm going to do is give you all the, maybe from these parts. Let me see where. Okay, from these parts, okay? From this. All right, then let me go back to, so let's see. If we see it is non-stationary, okay, we can we can detrain it if it is useful, okay. If it is not useful, usually we take the first difference. This is so far we learn, right? Now, we are going to talk about the third way, which is called co-integration. And this is covered in our textbook, okay? So let me use the definition of the co-integration, okay? Okay, let me see. Co-integration. Okay, let's see. Okay, this is covered in our textbook. Okay, and look at this one. After we do this Dickey-Fuller test, and then we find out that it is non-stationary, then what should we do? Since we say that for the regression analysis, we do need the variables are stationary. Okay, both y variables or x variables, all of them. Okay, but now if we find out that we don't have that, Remember the example we practiced last week about the data for the chicken consumption. Remember that? We practiced that data last week. Use the chicken consumption as a y, then chicken price, and also beef price, as well as the personal income as an x variables. And we find out that all the variables is non-stationary. Remember we do that example last week? Remember that? Well, okay, so in that situation, I wanted to run y and x. Then, since it is non-stationary, it is non-stationary. Therefore, the result of the regression is what? Spurious. Spurious, because all the variables are non-stationary. Okay, here, there's another way. Tell us that. Okay, let's see. If we find the time series is non-stationary, usually the traditional approach is to take the difference. Okay, so here I really say what is take the difference. So if I use, what's the first difference means? Using yt minus yt minus 1. So notation of delta yt is using yt minus the previous, the leg 1. So this is the first difference. Okay? The traditional approach is take the first difference, then put the first difference, the place of y as first difference, and the place of x as the first difference. Okay? But since originally I really want to see the relationship between the level of the variable instead of first the difference of the variable, right? Okay? So unfortunately, if we're using the first difference to correct for non-stationarity, then the economic informations, is not a relationship which covered in the theory, in economic theory. Because the economic theory usually is to say the original level of the variable instead of first the difference. The original y instead of delta y. Okay, so if you run, in order to meet the requirements of stationarity, then you replace delta y to replace y with delta y, or replace delta x as an x, then what? Then, all this theory is really not what we wanted. So usually, first the difference should not be used without carefully weighting the costs and benefits of the shift, and particularly, first the difference should not be used until the residual have been tested for this Okay. So this is what we wanted to do. So co-integration means what? Co-integration means matching the degree of non-stationarity of the variables in an equation in a way that makes the error terms, or we call residuals of the equation, stationary. And in that case, it will get rid of the spurious result. So what do we mean by that? Let's look at this one. Look at these two equations. The first one is 12.24. So originally, 12.24 tell us that yt and xt are non-stationary. Okay? So if we run these regressions, the result is spurious. However, co-integration is saying that after you run 12.24, then you do have the residual from 12.24. Okay? If you check this one, if you check the residual, if it is stationary. So in equation, ut is a function of two non-stationary variables. So if we can check if ut is a function of two non-stationary variables, so if we certainly expect ut also be non-stationary, but it is not necessarily the case. Particularly, suppose that xt and yt are related. Then if economic theory supports that equation as equilibrium, then departures from equilibrium should not be arbitrarily large. In other words, the ut is the residual, right? So it means that if xt and yt are related, then the error term ut may well be stationary, even though xt and yt are non-stationary. Understand what I'm saying here? Okay, although x and y are non-stationary, if in economic, if we really, confirm there's a equilibrium between x and y, then in other words, the ut is just a temporary departure from the equilibrium, which is not big. Therefore, if you test ut, if it is stationary, then the original regression model works. And this is what we call co-integration. Okay? All right? So if ut is stationary, then the unit roots in xt and yt have canceled out, and xt and yt are said to be co-integrated. Okay? Understand what I'm saying here? So do not worry. So worry about the non-stationarity of xt and yt, but also look at the residual of the yt and xt regressions. Then if the ut can pass the unit root test, okay, then if we can make sure the ut is stationary, then originally non-stationary result from the yt and xt can be canceled out. Then the result is not spurious. This is what we call co-integration. Okay? So we need to run this one. Okay? Then we do the Dickey-Fuller test on the residuals. Then if we are able to reject the null hypothesis of the unit roots in the residuals, then xt and yt are co-integrated, and OLS estimates are not spurious. So would you like to bring up the examples which we did last week, okay, to do the chicken consumption equations and check the residual of that regression to see whether the residual passed unit root test. Okay? That's using that as a practice. Did you remember that example? Which one? That's from the data is Chick 9 from chapter 9, CHICK 9. Can you download that data? Or maybe you have some of the data already in your notebook. So run a regression of YT as a Y, PC, PB, and YD as an X, and check the residual whether using the unit root test. If the residual passed the unit root test, then this is not the spurious result. Remember how to do that? Do you have the data? Yeah. Okay. Then check the residual. PC, PB, and YD. I don't think I have it now. You have to save the residual. Did you save residual? After you run the regression, then save the residual. Okay, let me see. Okay, this is the regression, right? Then this is the residual. Okay, we're at RESID. So make it U or EE. It really doesn't matter. E equal to RESID. Okay, then you have this U, right? E, then you use the unit root test to test this one. You understand what I'm saying here? Yeah, okay. So is it passed? Unit root test. So this is the E, right? So view unit root test. Okay? Usually we look at this trend and intercept, right? Remember that? Yeah. Okay, then maybe you try from 0 to see. Try it from 0 to see what happens. So what does this mean? It really doesn't. Yeah, okay. We wanted to see this is significant, right? Okay, so if you try the first leg, we just have like 30 something. Okay, so try 3. So, okay, 4. And I just try it. Then 6. Okay, 12. Look at 12, since it is annual data. Then it is. Look at this one. if you try lag 12, it pass, then unit root test. Since this is the annual data, we can try lag up to 12. Okay, this is what I say, co-integration test. Run the original regression, and we know that X and Y are non-stationary, right? Okay, then after you run it, you save the residual data and check the residual data using unit root test. Okay, then the whole procedure is called co-integration test. Have you done it in Python? Have you done it? You can try lag 12. Which variable? The residual of the regression. Yeah, we check the residual of the regression. Since the regression is Y and X all non-stationary, right? So I check the residual from that regression. So first of all, you need to store the variable of the residual from the original regression. Any questions, Bob? You mean this assignment? Due next week. Okay. No. The data is the one I show on the our iLearnings. Didn't I do that? TV. This one, yes. Where's the questions in the iLearnings? Didn't I put it iLearnings in the assignments? Oh, so you didn't see the questions yet? Okay. Let me show you the questions here. So you're not able to see from. Oh, I'm sorry. I thought you can see that before. Okay. This is my questions. Okay. This one. This is the questions. Okay. And you need to download data file which TB is already on iLearnings. Okay. Then I say answer following questions step by step. So first, this is a variable about the TB. Do you know what's TB? Treasury bill. Usually a treasury bill is the government bonds. So this is the data from United States federal government bonds. called treasury bill. Okay, then TB6 and TB3 means 3 months or 6 months. Okay, then plot TB6, TB3 series individually in the same diagram. What does the diagram look like? So this is what I call graphical analysis. Okay, look at the diagram to see whether they're stationary or not stationary. Okay, then test each series for stationarity. So you need to test the TB3 and TB6 whether it is stationary. So use the unit root test, including intercept and trend with various lag terms. I mean, you can try several lags. Okay, what do you find from this result? Okay, then test if the two series are co-integrated. So regress this one on this one, and time two. Okay, call it model A. Then use the unit root test, including non-exogenous with various lags terms. Okay, then is model A spurious result a regression? Then it means that you need to test whether this co-integration. Okay? So then after that, okay, I'll say something later on because my topic is not finished yet. Okay, there's some other questions, which is the ECM, which I want to cover just now. Okay, I'll put this one in our line groups. Okay, all right. Sorry, I didn't know that. Okay, I put in the iLearning groups. Okay. So up to question number 3, is there any questions about it? All right. So let's go back to the yes. Which one? You mean this one? Unit root test, including non-exogenous with various. This one means that you can none means none. Yeah. We have 3 options, right? We have 3 options, means none. Okay? And you can try various different lags to see the unit root test. Then what do you find the result? So this, now up to here, okay, this is called co-integration test. And up to this parts, this is called unit root test. Okay, so let me go back to the concept here. If I ask you, what's the difference between unit root test and co-integration test? What's the difference between these two? Okay, let me look at this one first. Tests for unit root are performed on single time series, right? And co-integration deals with relationship among a group of variables, each having a unit root. So that's the difference, right? Okay? Okay, and there's some summaries from our textbook say that there are some standard sequence of steps for dealing with non-stationary time series. Okay, this is from our textbook. Okay, I just make the summary here. Okay, the first one is specify the model. The model might be a time series equation with no lagged variables, or a distributed lag model, or a dynamic model. You all know what's all about, right? Then test all variables for unit roots. Test using the appropriate version of Dickey-Fuller test. Okay. Third, if the variable do not have unit roots, estimate the equation in its original units, means using x and y. Okay. Then, if the variables have unit roots, test the residual of the equation for co-integration test using Dickey-Fuller test. Okay. Number 5, if the variable have unit roots but are not co-integrated, means you test the residual, it didn't pass. Okay, then change the functional form of the model to the first difference and estimate the equation by first difference. Okay, if the variable have unit roots and also are co-integrated, then estimate equation in its original units. This is really obvious. Okay, so if we run the delta y and delta t, delta yx, yt or delta xt is really very, very situation which is, we have no other ways. We need to run the delta y and delta x. Okay? So this is the suggestion from the author, our textbook. Okay? I just make a summary here. Okay? Then using the idea of co-integration. Okay, if let me go back here. If I do see if this one pass, okay, if this residual pass, usually 12.24 is the regression called long run equilibrium by economic theory. So usually we do this in macroeconomics. Say in the long run, there's a relationship between x and y. Okay, then using that concept, I'm going to introduce. Therefore, we extend to another model. It's called error correction model, ECM. Then let's take a break for a few minutes. Then I'll come back to that topic. Okay? Okay, let's take a break.